Fifth type of reaction, acid-base neutralization, reaction between an acid and a base. And there are three types of acid-base neutralizations. The first type, Arrhenius. Arrhenius defines an acid as containing hydrogen and a base as containing hydroxide. Now the Arrhenius definition is simply a double replacement reaction, but it's a special type of double replacement where you get water and you get a salt. But you'll see where the charge is +1, -1, and we switch the positives, we switch the cations. So this is a double replacement reaction. If I give you an acid-base neutralization problem on the test, it will be the Arrhenius definition of acids and bases. Because the other two definitions, the Bronsted-Lowry and the Lewis, define an acid and a base differently, and we're going to spend a lot of time on acids and bases. So if you see one on the test, it will be Arrhenius. It will not be Bronsted-Lowry or Lewis. The sixth type of reaction, combustion, reaction of a substance with oxygen. If you react a metal with oxygen, you get a metal oxide. If you react a nonmetal with oxygen, you get a nonmetal oxide. Both of these reactions use the most common charges. So magnesium +2, carbon +4. And these are also combination reactions because I'm producing one product. If I combust a compound containing carbon and hydrogen, or carbon, hydrogen, and oxygen, the products will always be CO2 and water. So let's look at a couple combustion examples. First one, I'm reacting aluminum with oxygen. Oxygen is diatomic. Put them together, we're going to use the most common charges. Aluminum +3. Oxygen, most commonly, -2. So my product, Al2O3. Then you can go back and balance that chemical equation. If I combust glucose, react it with oxygen. It's a carbon, hydrogen, oxygen compound. It will always produce CO2 and water. Then I could go back and balance it. 6 carbons, 12 hydrogen. I already have 6 oxygen in glucose, so the coefficient in front of O2 is a 6. Seventh type, redox reactions. Now we've already covered redox reactions, and we will have a test specifically on redox reactions, so we're not going to worry about this type of reaction for this test. So we're going to skip all of the redox. We're going to go to number 8, complex ions. Complex ions are weak electrolytes. They're ordinarily formed from transition metals, aluminum or beryllium, combined with several ligands. A ligand is simply an anion or molecule that has a lone pair of electrons, and we're able to form coordinate covalent bonds back to the metal. So these ligands bond to the metal, whether it be a transition metal, aluminum, or beryllium. The number of ligands that bonds to the metal is called the coordination number. Anytime you have water as a ligand, the coordination number will be 6. Otherwise, metal ions with a +2 charge have a coordination number of 4. If the metal has a +3 charge, coordination number is 6. So what are some common ligands? Here's a list of some common ligands. So anytime you see a transition metal, aluminum or beryllium, reacting with one of the following, it will be a complex ion. Now, I'm going to make this easier for you. The only 2 ligands that you will see on my test are water and NH3. So if you see a transition metal, aluminum, or beryllium combined with these 2 ligands, it's going to be a complex ion. For example, we're reacting concentrated ammonia with nickel 2 chloride. Nickel is a transition metal. I'm reacting it with ammonia. It's going to form a complex ion, which means NH3 is going to bond to nickel. Now the number of NH3s that bond to nickel, since nickel is a +2, is 4. So the coordination number is 4. Nickel still has a +2 charge, Ammonia is neutral. So that's what the complex ion looks like. The coordination number is 4. Where did the chloride go? Chloride is still there, but it's not part of the actual reaction. So I kind of leave the chloride out because it's not part of the complex ion. I'm going to do a couple more examples, and these are not on your notes, but you can certainly add those. Zinc chloride is added to water. So you got a transition metal, zinc. We're adding it to water, common ligand. So zinc will bond to water, and the number of waters that will bond to zinc, since it's an aqua complex, is 6. The coordination number is 6. Zinc is a +2, so this complex ion is still a +2 charge. And again, the chloride is still there, but it's not part of the reaction, so we kind of leave it out. This next one, AlN is added to ammonia. Aluminum is a +3. We're adding it to ammonia. So we have aluminum with a common ligand. Since aluminum is a +3, the coordination number will be 6. And we're going to put the +3 charge out here. And again, the N is still there. It's just not part of the complex ion. The 9th type, anhydrides. And anhydride literally means without water. So it's a compound derived from something else by removing water. An acid anhydride is a compound which, when added to water, produces an acid. So in this example down here, SO2 is an acid anhydride because when I add it to water, it produces an acid, H2SO3. Now, by the way, this is a combination reaction. SO2, the charge on sulfur was +4, so sulfur is a +4 over here. This is a combination reaction as well. We're just using different terminology. A basic anhydride is a compound which, when added to water, produces a base. And these tend to be metal oxides. So when you have a metal oxide, like sodium oxide, you react it with water, you get a base, NaOH. This is also a combination reaction. We're just using different terminology, and we're calling this an anhydride. So when nonmetal oxides react with water, the product will be an oxyacid. Same charges on both sides of the equation. When metal oxides react with water, the product will be a base. So write the chemical equation for the reaction that occurs when water is added to calcium oxide. So we have CaO plus water. Now this is a metal oxide reacting with water, so the product will be a base. So Ca with OH, balanced charges, CaOH2.